Hi, welcome back to one more video on SLE4428 and SLE5528, and this time using the OMNIKEY 3121 reader writer. This OMNIKEY 3121 reader writer is manufactured by a company called HID Global. I have made a similar video but using a different reader writer, that is the ACR38U and ACR39U, which is from the company called ACS. And this video is available in my YouTube channel, and I have covered everything in depth in this video. So if you have the ACR series of reader writer, then I would advise you to see my other videos. If you go to YouTube and search SLE5528 programming, or if you directly type the Farnet Pi videos, you will see this playlist, and I have made 9 videos. And if you look at this the video called Understanding 4428 5528 part 6a and the next part 6b, I have covered enough for the ACS reader writer. So in this video I'm going to show you some of the features of the 4428 and SLE5528 cards. This card has got 1024 bytes of EEPROM. It has got 1024 lock bits, so that is every byte can be locked, and this is a one-way or one direction locking. So once the byte is locked, you cannot unlock it. It has got 2 bytes password, or also called as some kind of a presentation code, and this is nothing but a password, and that is a 2 byte. And this has got a 1 byte of error counter. So here 1 byte doesn't mean the 255 or 256 values, so it means you can have 8 tries for the wrong password. After that, the card will completely lock itself and becomes read-only. And you're going to need this documentation. Always keep these documentation handy. This is SLE4428, SLE5528, and if you have the OMNIKEY 3121, then you will need this documentation for the developer's guide. And I'm also going to compare some of the differences between the ACR39 series and the OMNIKEY the 3121. So in this video I'm going to show you how to get the ATR of SLE5528. This also applies for SLE4428. You're going to see how to do the read operation, how to authenticate and write, and you have to authenticate before you write. So after that I'm going to show you how to change the password, also called as the PSC code, and we're going to see how to log the individual bytes and how to change the error counter. This is something every software project does. And you're going to make the tag read only. Basically it also means it's like a destroying the tag. So in order to carry out all these by yourself, you need a brand new SLE4428 or SLE5528. So if you want to buy SLE4428 or 5528, you can visit this website called packsupplies.co.uk, and you can find so many types of contact cards here. And in fact, so I found it very difficult to buy SLE5528 from internet, but now so all these type of tags I can buy from this website. Now this is the first document you have to read. It's called the SLE4418 or SLE4428, and this document explains you what this tag is, the memory organization and various commands. However, these documents have got some useful information, but they're not very easy for developers to program. So say for example, if you look into the documentation, most of the things are explained using these types of the wave diagrams. Okay, and also using these raw commands are also not very easy. So for that reason, it's very easy for us to use these type of tags using some branded reader writers like ACS39U or this OMNIKEY 3121. However, read this document has got a very useful information. And the next document is SLE5528. You don't see much in this document because most of the functionalities of 5528 are same as 4428, and you can see some additional stuff here. It speaks about the speed, and there is some kind of a like electronics difference between 5528 and 4428. But however, a feature or the functional wise, both are same. It has got a nice diagram here that shows, if you see this diagram here, it says the read is always possible. You don't need any password verification. However, in order to lock the bits, lock the bytes, or in order to write something to the memory, or change the error counter, or anything anything you want to change, you have to go through the password verification. The other document you must have is this OMNIKEY 3121 developers guide, and I have used all these commands mentioned in this document, and also it's very easy to understand. This document is easy. So I'm going to show you how I have used these commands. I have used the command, the read binary command. I have used the update binary, this to change the EEPROM content. I have used the verify. This is to authenticate, unit verify, and to read the protection bits, whether to find out whether the byte is locked or not locked. You can use read protection memory, and also it's clearly mentioned here what it does. And this is if you want to protect, so you're going to use this compare and protect command. And the modify, if you want to modify the password or PSC. And if you compare look at that, modify command is so easy with the reader writer. If you go back to the original documentation, modifying the password is a very lengthy process, and also it's more of a playing with the bits and bytes here. So one more reason why I made this video using OMNIKEY 3121 is it's mainly because of the cost. So you can buy OMNIKEY 3121 reader writer for less than £10 these days, and this is not the latest reader writer. There are so many latest reader writers from the HID which can be used with the SLE4428 or 5528. However, for a student or for a hobbyist who doesn't want to spend more money but want to learn how to use SLE cards, probably 3121 or the ACR39U would be the best choice. I've connected my OMNIKEY 3121 reader writer, and I'm going to insert a new SLE5528 card. And this feature is available in version 1.4.3 of this learning kit. If you do not have the learning kit, so even then you're going to learn or you're going to get some knowledge out of this video. So don't have to worry if you do not have the learning kit. If you look at the release notes, so there are a few changes in this version. So the first thing is there's a small improvement done in reading the data. Before this version, keep in mind this tag has got 1024 bytes of memory, and I used to read 16 bytes at a time. I've changed that to read 128 bytes. So the reason is if you can read more, so what's the point in reading less? So this is something, a feature already there, and also this is also going to make the reading faster. you can now directly modify the error counter, and that is in this version. If you look at this, what the documentation says, the error counter can always be written. So looks like you don't even need authentication. So that is maybe something special. I'm going to show that these things can be done. And also I'm going to read the production bits 256 bytes at a time. Again, this is a faster read. Before this version it was reading 16 bits at a time. Obviously this is a faster read, and you're going to see that that's what this video is about. Reading and writing to SLE5528 using OMNIKEY 3121 is added here. See, this software works for both ACR39U and the OMNIKEY. And I'm also going to, there is a small difference between OMNIKEY and ACR, and that difference I'm going to show you in this video. So first thing you do is get the readers connected, and this is a standard PCSC type of command that are used here, and you should see it's OMNIKEY Cardman 3x21. First thing is the connect. Now based on the ATR, so if you click this button, get ATR, this is the ATR. Now before opening this screen, what the software, when it hit this connect, what it did was, so it reads the ATR from the tag, and if the ATR matches this number byte to byte, so obviously the software knows it is a SLE5528, so it opens the screen. Now the card is already activated. It's all done by the OMNIKEY reader writer, so there is no special command to activate. The first thing is hit this button, read data. This is going to send a series of read commands to bring the data from the tag into the software. If you click on the commands tab, you can see these are the commands, and I'm reading 128 bytes at a time, so you'll see so many such commands here. So the first command is the read memory command. If you look at this structure, the command bytes FFB00080, so that matches what the documentation says. This is the bind read FFB0, because the address bytes are addressing done by 2 bytes, the MSB and LSB, and you just have to specify how many bytes you want to read. So I'm reading 128 bytes at a time. So this is what it's all about. So after reading the data, so I'm using the read protection memory. So in order to populate in this screen, the left side is where you see the data, the right side corresponds to the protection bit of individual byte. Say for this byte, which address 0, the protection bit is this, and for any byte you take for this byte, so this byte is in the row 0048. In fact, the values on left side, these are the addresses, okay, in a block of 16 bytes. So you got address 0, address 1 up to address 15, after that address 16, and goes up to address 31, and so on. So just have to map the corresponding byte here to this the corresponding bit. So what the software is doing, it's just reading the 1024 bytes by sending the PCSC commands, and also it is reading the protection bits. But the protection bits, this is something different, what the documentation says. I'm going to explain this in later videos. You could see that I'm reading 18 bytes at a time. It's a very odd number. When you read 18 bytes, I still can't figure out what the problem is. However, if you read 18 bytes, I get the 16 bytes with value 0, and bear in mind, a new tag doesn't have any locked bytes. Every byte is writable. except the memory, sorry, the password. Everything is writable. So these values should always be zeros. So however, I'm not very sure why I always end up getting 2 ones. So if I read 16 bytes, I will get 14 bytes with zeros and 2 bytes with 1 and for that reason I'm reading 18 bytes and ignoring these last 2 bytes. So likewise, you just have to keep on reading in a loop until you finish reading for 1024 bytes. Again, there is some peculiarity in reading the last page where so if you look at the since most of the things are covered in my early videos, I probably jumping a little bit. In SLE5528, the last 3 bytes here, they are not data, but they are the error counter followed by 2 passwords, and you can never ever read the value of this password. And for a brand new tag, the password is FF. So that's what we have done so far. We have just read the value of the memory and read the value of the protection bits, and I'm just populating these 2 grids. And in fact, I have shown deliberately the last 2 bytes that corresponds to the password. I've shown them as a ticked. In fact, you don't get them as a protected when you read it, but I've just to make it consistent with the ACR 39, I made them as a ticked. And keep in mind, you cannot ever read the password. So that's what we have done so far. The next thing is, how do we write? Now the documentation says, and that's a feature of this chip, you cannot write without any without the password authentication. So I'm going to write here, I'm going to just scribble, or I'm going to, best thing is click on E, so I can put a nice sentence here, say SLE5528 / SLE4428 is okay. I can't write more than that. So this dialog box stops you from entering more than 16 characters. Okay, now I'm going to clear off all these commands, and if you hit this W, this for reading, sorry, this for writing. If you hit W, so it says, this is just a warning given by the software. It's just telling you that for SLE4428 write does not work without PSC authentication. So there's something password authentication. If you click OK, it still continues to write. And if you look at this, the outcome, and I have used the command, the update binary. If you go back to the documentation, this is the same command what documentation says, update binary. So you just have to send the FFD6 followed by 2 bytes of address here, the MSP LSP followed by the data, and depending on how many bytes you write, the LC will be set to the value. But since I'm writing 16 bytes at a time, the LC will be 16. And if you look at the outcome, if you look at here, so if the write was successful, the value will be 9000. This is a standard status code for any ISO 7814 command, but I'm getting 6982. If you go back to the, so one good thing about is everything you need to know is in this documentation. So it's 6982. So I'm just going to zoom this a little bit. So this says security status not satisfied, no pin presented. So this is exactly what has happened with us now. We try to write without authentication. Now I'm going to authenticate. So now to authenticate, you have to key in the values here, and this is the lower byte of the authentication code, this is the higher byte. So I know this is a brand new tag, and this is the default password is all FFs. In fact, when you buy a new tag, all these memories are set to FFs. So there's something, there's a technical reason behind that. So I'm going to leave that the documentation I showed you and explains what it is. Now I'm going to authenticate. Now when you click authenticate, you got a nice message here, and also the button is turned into green. If you look at these commands, I'm sending the verify command, and this is the command structure. You have to send what is the password, and you get a positive response 9090. So look at the verify command. Now again is explained here. It says this is the command used to authenticate both SLE4442 and 4428, and on success we got a success. If the password were wrong, I'm going to show you that sooner, you will get a different error code. Now we are able to authenticate. Now we should be able to write this data. If you look at in ASCII mode here, you can see we wrote this this data in starting from address 32, and if I hit W, now the write data is okay. And if you look at the command, the update binary which failed before with the status code 6982, this time we got 9000. So you want to check that again. So probably I'm going to take out this tag and put it back. Connect, read. So keep in mind, for reading you don't need any authentication. Look at that. This is what we wrote, and it is written. So write is successful. So the next thing will be about how do we protect. Now there is a small problem in protecting the bytes. I'm not very sure. It's something to do with the 3121 or so. What I've done is I've sent a message to the support of HID. I'm just waiting for the reply. Now if you have seen my video on SLE, so using this tag using ACR39U, you might have noticed the reading, writing, locking, everything works without any issues at all. But here there is some problem. Probably the best thing to do is not to discuss protection at this time. Probably we can see the other bits here. What happens if the password is wrong? Now I'm going to clear all these logs. I'm going to authenticate with the password, say F1. Now just keep an eye on the error counters here. So at present error counter says you got 7 tries left. In fact, again there is a small issue here, but let's not worry too much about that. Now in theory a brand new tag should let us have 8 tries, but if you read the value of this now if you remember this byte here, the third byte from the end, which has got 7F. Now 7F tells us how many retries I can do. So you just have to count how many 1 bit are there. So if you convert hex 7F to binary, you'll end up getting 011 1111. So each ones will tell us how many retries you can have, how many wrong password you can enter. Now based on this, I'm showing the value, but if you read the documentation, it says a brand new tag will have 8 retries. So what I'm going to do is just authenticate with the wrong password. Now authenticate. Now you got authenticate error. If you look at this command, it says we are still using the verify command, but this time the output is 63 and 86. The best thing is the documentation. Look at that. This is so simple. See, the documentation we got 63 and C followed by some number. So it says if you get this as the status code, the X tells us the number of further allowed retries. Now in theory I should get 7, but if you go with this number, it's 6. So based on that number, I'm just populating this drop down list. So it's nothing I can do here, but I did try. You can't go more than 7 wrong retries. Your card will get locked. Probably we're going to see that. Try again. So F9, authenticate. Every time you enter the wrong password, you'll keep getting one less than the previous. Now I'm going to try 00, authenticate. You got 4 retries. 11, authenticate. 12, authenticate. You got 2 retries. 13, 15, authenticate. I can't do any more mistakes now because this card will become useless. Now this time, so I have to be very careful. I have to put the right code. Authenticate. I got a green. You know that when you get that 90, so I'm setting the value as success and 8 retries left. And also I can read just the last block. If I click on this read command, you can see that once the password is authenticated, you are able to read the password. So you're not breaching any security here because you already know the password. So you're just showing, the command is showing you the data that's written in this 2 bytes. And also, if you look at this, the error counter byte, it is now all FFs, so that will give you 8 ones. Based on that, I made a simple statement here saying that you got 8 retries. Again, keep in mind, you do not get 8, actually you'll get only 7. I'm not very sure whether it's something to do with the hardware or or that's the way it works.